Welcome. I am Jinying Dong, Assistant Professor in the Faculty of Electrical Engineering, Mathematics, and Computer Science at Delft University of Technology. This lecture takes a close look at inverters and the important role that they play in an EV powertrain. The learning objectives of this lecture are as follows. First, we take a look at variable frequency drives, or VFDs, and understand why they are an essential part of EVs. Next, we understand what inverters are and how they are constructed. After this, we look at the elements of an inverter, their modulation to achieve a variable frequency drive, and finally, the main performance indicators of an inverter. The first thing we need to understand is, what are variable frequency drives? They can be defined as a drive system that controls the speed and torque of an AC machine by varying the input frequency as well as the amplitude of the voltage or current. As discussed in the previous lecture, the current in the state windings induces a rotating magnetic field. The speed of this rotating magnetic field is called the synchronous speed and can be related to the frequency of the input current and the number of propairs of the rotor as 60 times the frequency F divided by the number of propairs P. The voltage induced due to the rotating magnetic field is given by the formula E equals K times omega, where omega is the rotor angular speed and K is the induced voltage constant. Therefore, as we can see, in order to control the speed of the machine, both frequency and the voltage amplitude have to be varied. Same as the electrical machines, the VFD in EVs should also be bidirectional. As has been mentioned in previous lectures, an electrical machine can run in two modes. Motor mode, where it takes power from the battery or in generator mode, where it delivers power to the battery. For the motor mode, the VFD operates as an inverter converting DC power to AC power. In the generator mode, the VFD operates as a rectifier and converts AC power back to DC power. The circuit on the slide depicts a three-phase voltage source inverter, a device that can be used to convert DC voltage from the battery into the three-phase AC voltage to the electrical machine. The circuit consists of two main components, a DC bus capacitor bank and power semiconductor devices, the function of which will be discussed presently. The DC bus capacitor bank operates as an electrical energy buffer and is used to stabilize the DC bus voltage so that sudden changes in the load will not cause large voltage ripples. The power semiconductor devices work as switches, turning on and off the high voltage and large current so as to produce the variable frequency, variable amplitude, three-phase supply. These power semiconductors are operated by low voltage electrical signals, which makes them suitable for digital control. There are other components that are generally a part of the inverter circuit. The first among these are output filters, which can be used to suppress counter ripples in the machine winding, or to protect the machine insulation by reducing the voltage switching rate dV/dt. Gate drivers are circuits used to switch on and off the power semiconductor devices, while sensors and controllers are used for the digital control of the electrical machine. Lastly, there is generally a heat sink present for heat dissipation. The figure on the bottom right shows an example of an inverter in practice. After the voltage source inverter, let's take a look at power semiconductor devices. There are many types of semiconductor devices in the industry, but let us focus on two most widely used ones, power IGBT and power MOSFET. The collector emitter terminal in IGBT and drain source terminal in MOSFET are the power terminals where the main current flows. The gate terminals in both are responsible for turning on or off the current channels. In IGBT, the gate terminal is also referred to as the base terminal B. IGBT stands for insulated gate bipolar transistor. When gate voltage VG is greater than the emitter voltage VE, or the base to emitter voltage VBE is greater than a threshold value, the IGBT will conduct the path from collector to emitter, make IC almost equal to IE, and the collector to emitter voltage drops down to a very small value. When VBE is less than the threshold value, the IGBT will not conduct, leading IC to almost 0 ampere. Since the IGBT can conduct in only one direction, the anti-parallel diode is needed for reverse current flow. It has a medium switching speed that ranges from nanoseconds to microseconds. Due to their capacity to conduct a large current at high voltage, they usually have high ratings. MOSFET stands for Metal Oxide Semiconductor Field Effect Transistor. MOSFET starts current conduction when gate-to-source voltage VGS is greater than a threshold voltage. The drain-to-source voltage during conduction is drain current ID times IDS on, where IDS on is the resistance between drain and source terminal when the MOSFET is on. When VGS is below threshold voltage, that IDS on tends to be a very light value, and hence the MOSFET is switched off. Unlike IGBT, MOSFET has an internal body diode for reverse current flow. In terms of switching speed, it is also faster than IGBT and has a switching time in nanoseconds. The voltage and current ratings of MOSFETs are generally lower than that of IGBTs. Both semiconductors can be simplified with ideal switches, as shown here when examining their external behavior. In practice, they are available as either discrete devices or a module with several devices packed together to form a building block. Let us now look at how to use power semiconductors to form the basic building block of a three-phase inverter, which is a half-bridge inverter. As shown previously, the power semiconductors can be simplified as ideal switches, so this half-bridge circuit can be simplified as two switches S1 and S2, connected in series across the DC bus. The input DC voltage is converted to an output AC voltage between the two switches by switching S1 and S2 on and off in a complementary way. VDC is the input voltage and VAN is the output AC voltage. When S1 is on and S2 is off, the output voltage VAN is equal to input voltage VDC, and the voltage across A and the midpoint of the DC bus VA0 is 0. When S1 is off and S2 is on, the output voltage VAN is 0, and VA0 is minus VDC divided by 2. Therefore, in one entire switching period Ts, S1 is on and S2 is off from 0 seconds to D times Ts seconds, and S1 is off and S2 is on for the rest of the switching period. Repetition of the same switching period provides the waveform shown in the graph. Then we can calculate the average output voltage VAN is D times VDC, and the average VA0 is D minus 0.5 times VDC, as indicated by the blue line in the waveform. To achieve an arbitrary required average voltage, we can vary the duty cycle D. A technique called pulse width modulation can be used, as shown in the waveform on the bottom, two waveforms are considered: a reference waveform noted by Vref and a triangular carrier waveform. When the reference voltage is greater than the carrier voltage, S1 is on, and when the carrier voltage is greater than the reference voltage, S2 is on. Therefore, by adjusting the reference and the carrier waveforms, the duty cycle D is automatically obtained to achieve the required voltage output. The previous slide shows the half bridge can be used as a converter to vary the DC output voltage, that is to say, a DC-DC converter. However, it is possible to be operated as a DC to AC converter or a single-phase inverter as well. To generate a single-phase AC output, the reference waveform for the pulse width modulation should be a sinusoidal waveform, and the carrier wave frequency should be much higher than that of the sinusoidal frequency. Only in this way can the average output in each switching period follow the sinusoidal trend. Here it shows the modulation process. As we can see, the duty cycle varies sinusoidally following the reference frame. In each switching cycle TS, the average voltage VA0 would be close to the average of the reference voltage Vref in that cycle. If the switching frequency is much higher than the reference AC frequency, there will be many switching cycles in one AC cycle, making the averaging approximation more accurate. The output voltage will not be a replica of the reference voltage, but contains harmonics caused by the direct switching. These harmonics will have limited impact because of the filtering of the inductive behavior of the electrical machine winding. The fundamental component of the output voltage can be calculated by modulation index M times VDC divided by 2 times sine of 2 pi t divided by AC voltage period t. The modulation index is a quantity to present how large the reference is compared to the available DC bus voltage. A three-phase inverter can be constructed from 3 basic half-bridge building blocks. The operation is similar to the half-bridge, but now we have 3 phases instead of 1. 3 sinusoidal reference waveforms will be generated now, and the carrier waveform will be common for all of them. The fundamental components of the output voltage for each phase UVW is shown on the right. The variables parameters in the equations are AC period T, modulation index M, and phase angle phi. The variation in T results in variable frequency, and the variations in modulation index leads to variable maximum output voltage. For these reasons, the inverter can be used in variable frequency, variable voltage drives. The performance of an inverter can be evaluated based on the following criteria. The switching frequency is the speed at which the power semiconductor devices are able to switch between the on and off states. The maximum DC voltage of the inverter is determined by breakdown voltage of the power semiconductor devices and the capacitors. The output AC voltage range is dependent on the available DC bus voltage and the modulation method used. The frequency range of the AC output is decided by the switching frequency, the modulation method, and the controller capability. The capacity of an inverter is the amount of apparent power that the inverter circuit can handle. The efficiency is defined as the ratio of the output power to the input power. The input and the output are decided based on the direction of power flow. The efficiency varies as per the operation condition, that is to say, varies according to the torque and the speed of the electrical machine. Therefore, the efficiency of inverters along with electrical machine can generally be depicted in an efficiency map as shown below. That's the end of the lecture on inverters. In the next lecture, we will learn how to use the inverter to implement the control of the electrical drive.